Is my screen visible to you guys? Okay, thanks for confirming. Yeah, so good evening, people who have just joined. And my name is Amritanshu. I am a PhD student at IIT Kanpur. I am currently in my third year, and I work in the domain of robotics. Specifically, I work on legged robots. So I work on developing control algorithms for quadruped robots. That those are four-legged robots, which you might have seen in many online videos. So I work on developing algorithms which help these robots to work on different kind of environments while maintaining their stability and balance. So that's my short introduction. And yeah, so I will be taking this weekly discussion session every Sunday 3 to 5. And so we will conduct the session in a way that I will cover the topics which have been discussed in the previous week, and I will choose specific topics which I think might need some more attention and might need explanation once again to get into some details. And then I will discuss some questions which will help you to grasp those concepts better and then help in solving your assignments and examinations. So before I begin, so if you have any specific questions regarding the content that has been covered, you can just let me know and I will be happy to discuss that first. So yeah, please feel free to go ahead and ask questions. Or just any one of you can just quickly summarize what have you studied or seen in the lectures till now. Any one of you. Okay, yeah. Mm-hmm. Okay. So, were you able to basically understand and grasp all the concepts that have been discussed yet? Especially like once the technical terminologies of description of robots start, basically joints, degrees of freedom, and then the transformations where the we get into rotation matrices and homogeneous transformations. Someone's microphone is open. Can you please turn that off? Okay, thank you. Okay, anyways, let's get started. I will briefly summarize what has been discussed, and then we spend some time on the mathematical preliminaries. Okay, yeah. So let's begin. So this is week one. Yeah. So first thing, which has the name of the course goes by, that this course is about robots, right? And understanding how robots, basically how to describe robots in a mathematical way, and then how to develop algorithms in order to control those robots. So, yeah, definition of robots, many different varieties of definitions are there. Robots are programmable entities, right? And they can be reprogrammed. That's one key thing which we need to remember. And there are many different types of robots which you might have already seen, right? And they can be distinguished on different criteria, basically. So one such criteria is series versus parallel, which has been covered in the lectures also, right? And so I will also keep referring to the uh, lecture slides as well in between to just refer to images which may be too difficult to draw, or my drawing could be too bad to draw them again. So I would just keep referring back to the slides for those images. Yeah, so as I mentioned, series versus parallel robots. So series robots have a fixed base, and then there is a links which are each joined to one link, the link before them and the link after them. So it's a sequence of links, and at the very end is an end effector. In parallel robots, we have loops, so it's not a open kinematic chain, but it's a closed kinematic chain. Basically, uh, in those kind of robots, at least there are some of the links which form a closed shape, basically. So that is one key difference. Most of the robots which you encounter are series robots, and parallel robots are, I would say, slightly less popular. Okay, uh, okay. One more type of robot which I would like to discuss here, which basically does not entirely fit into the description of series versus parallel robots, uh, but can be thought of as a combination. So what we call as floating base robots. So has anyone heard this term before, floating base robots? Okay, so you have seen the series robot. So that's basically your classic manipulator or robotic arm, right? In which there is a base link, and then there are consecutive links which are joined using revolute or prismatic or any different kind of joints that exist, right? So this is link one, this is link two, and this is link three, and so on, right? Now, floating based robots, first of all, are basically they are commonly used to describe the mobile robots, and especially since this is relevant to the domain which I work, legged robots. So I'll just quickly draw a robot with four legs. Right. So what's special in this case? So first, let me tell you where is the series robot in this robotic dog. So this is a very basic sketch. So this is the body or the torso of the robot, right? And these are the legs. So there are four legs. So each of this leg, they are basically an example of a serial manipulator, right? This one leg, if you just see, because there is a joint here, there is a joint here, right? So there are four such series robots, right? And the key difference between a robotic arm is that this is mounted on a fixed base, right? So which is mentioned here also, right? Serial robot, a fixed base, and then the links and joints are connected sequentially. Now, if we mount these serial robot not on a fixed base, but a base which is free to move, right? Basically, a base which can translate and rotate. So it has basically this base has additional 6 degrees of freedom, right? So this this center of mass of this base, it can move in all the three directions, right? Let me just use a different color. So it can move in this, uh, let's say, x, y, z direction, and it can also rotate about these axes, right? So what happens now is that the base on which these serial robots, you can imagine four serial robots attached to the four corners of this base. Now the base doesn't remain fixed and the base is mobile, right? So first of all, that makes this robotic system a mobile system because of course it can move in space. And the second thing, which is the floating part. The floating part is that the base has additional degrees of freedom. It can be either translatory or rotatory. In this case, for a mobile robot like a robotic dog, a quadruped, or in fact a humanoid, right? These have 6 degrees of freedom for the base, so they can just move anywhere in the space, right? So uh, this is this is something which you can keep in mind about the term floating base robots. Right. So, so yeah, next comes the again a very common term which we will use, in our day-to-day discussion of robotics is degree of freedom. Right. So, so mathematically speaking, it's basically the number of parameters that the number of independent parameters that are required to uniquely specify uh, the configuration of the robot, basically. So that might sound a little bit not that might sound a little bit unclear. So let me just put it and use an example to clear that out. Right. So let's start with our uh, classic two-link serial manipulator. Right. So there's a joint here and there's a joint here. Right. So I believe you all know that uh, if how many degrees of freedom are there in this system? Can anyone just quickly let me know? In this, how four? Can you just let me know how did you count four? Ah, yeah. So that's not correct. I will tell you how it's not correct, right? So basically, I drew this axis, right? This is x-axis and this is y-axis, right? Now the this is the, let's say, the end effector, right? Now let's say the position of the end effector is given by this point P, and of course, since this is a planar robot, basically the plane in which I'm drawing this robot, it always remains in that plane, right? It does not come move out of that plane. Okay, so the position of the end effector would be fully described by these two quantities x and y, correct? Right. So so this is your first thing which you can try to identify, that how many parameters you would need to describe the position of the or the configuration of the robot, right? So the thing is that this is a and let's say for this case these both are the revolute joints. So the first joint can move like this, and let's say the angle is given by theta 1, and the second joint is able to move like this and the angle is given by theta 2. Okay, now once I specify theta 1 and theta 2, let's say if I specify theta 1 is 30 degrees and theta 2 is 60 degrees, right? Once I specify theta 1 and theta 2, I know the exact configuration of the robot and I do not need to specify anything else in this case to basically know where my end effector lies, right? So two parameters are sufficient in order to specify the position of the end effector or the configuration of the robot. Now, the way you answered is that the first link can move in XY direction and the second link can move in XY direction, right? Now the what w- now if you would look those two links individually, okay? If you look at those two links individually, let's say we disconnect them, okay, and disconnect them like there are from this joint also. So let's say I just pull off this link from this joint and then disconnect this joint also. Right. Now this is just imagine a rectangular link lying in that plane. Right. Now the center of mass of this link can be, let's say, expressed by x2 comma y2. Right. Since we are considering a planar problem, we are only working with two coordinates, and this is x1 comma y1, right? So this is the position of center of mass of the first link and position of center of mass of the second link, right? And this is the origin 0 comma 0. Okay, now the way you thought was in these terms that okay, two links and both can have xy coordinates, so add both of them, so 2 plus 2, 4 degrees of freedom. But what is not considered in this kind of a thought process or chain of thought is that the links are connected. They are not independent to move, right? So we have two joints, right? And the joint, what it does, it constrains the way in which these links can move, right? So it's not possible that I can arbitrarily move the second link anywhere in the space while also ensuring that the links are joined, right? Am I clear in my point? So mathematically speaking, what happens is that uh, basically the joint here, let's say J2, and the joint here, J1, what happens is that these two joints, J1 and J2, these two joints, these joints, they constrain the system, right? So joints are what? Joints are in a way constraints, right? Joints are constraints on the way the system can move, right? So individually, this has 2 degrees of freedom and this has 2 degrees of freedom. But when they are joined, when these two joints are active, if I say, then this takes away 1 degree of freedom and this takes away 1 degree of freedom, right? In fact, Uh, and in this case, I have not also considered the basically I've just considered the center of mass of the system. If I consider the entire link, then I should also add one more variable here, the orientation of the link. So phi 2 and phi 1, right? So if I consider this as a proper extended body, then the center of mass position and the orientation of the link. So all three can vary if the link is considered independently, right? So let me just add 2 translation plus 1 rotation, 2 translation plus 1 rotation. So these two links independently have 3 degrees of freedom in the planar case, right? Now, as I mentioned, and then these two joints, which I can also show you how these two joints take away the 4 degrees of freedom. They are constrained by these joints. So it's basically 3 plus 3 due to these two links, right? And due to each of that revolute joint, 2 degrees of freedom each taken away. So the total system, this 2R, which we said this 2R manipulator. Manipulator. This 2R manipulator has, as the name suggests, 2 degrees of freedom. Right. Now, let's just spend some more time on it and see how these 2 degrees of freedom are taken away. Okay. So, is everyone with me till here? Any questions till here? Did you under? Okay. I think there is. Okay. Thanks for the confirmation. So, what we are discussing right now is how what we're discussing right now is how basically individual bodies which have 3 degrees of freedom in this planar scenario, how when we connect them using joints, the number of degrees of freedom they reduce, and how we can arrive at the final degree of freedom for this 2R manipulator system. Yeah. So let's continue with the discussion. So the first, this is the link one, right? And it's basically position and orientation, which I am collectively denoting as P1. This vector is x1, y1, and phi1, right? So this you can imagine be anywhere in the xy plane, and orientation can be anything between 0 to 2 pi. Okay. Now just consider adding the first joint. Okay. Now this is the these are the axes. Let me choose some other color. Right, and let's say this is the link, but with a connection here, with a revolute joint here, J1. Okay. Now what effect that does this J1 have? So first thing, what type of joint is this? So here we are considering a revolute joint, the most common joints you would see in the robot world, right? So revolute joint allows rotation. It has 1 degree of, it has basically, again I will say how, I will show you how it has only 1 degree of freedom. So it has 1 degree of freedom, allows rotation about one axis. Okay. So this allows rotation, this a revolute joint allows rotation about a single axis. So if this is the link, and if the axis is along this direction going into the uh, plane, then this is how the motion would be, right? This is a revolute joint's motion, right? You can imagine like this. So now, as you would imagine, if I have a revolute joint here, it can only rotate about the z-axis, which is coming out of the plane, right? This is x and this is y, right? And now the center of mass of this body, of this link one, now it can only move in a certain way, right? Because it is constrained to this joint, it can only move along this circle, right? If I rotate, if this joint is free to rotate 360-degree, then the path of the center of mass would trace what shape? It would trace a circle, right? So now it is, we cannot vary x, y, and phi independently. Okay, so all these independent variables, which was the case when the link is not attached to any joint, now they have a relation among them. And once a relation is established between two variables, they do not remain independent anymore. And the consequence of that is that the system can now be described using a lesser number of variables which are independent. So what we can write mathematically in the same thing which I just described, if I write mathematically, then let's say the center of mass is at a length L1 by 2, uh, right? So then this location of the center of mass should satisfy the equation of a circle, right? So x1 square plus y1 square should be equal to, it must be equal to this, right? So this is the equation of the locus. Locus is basically the path of the center of mass. Okay. So so now whatever value of whatever be the position of the center of mass, it must satisfy this relation. If it does not, then it means that basically the joint would not be joint is not physically enforced there, right? If the center of mass of the this link is here, right, then obviously it means that we have physically removed this joint, then only it can the center of mass can reach this point, right? And the same if it lies anywhere except this circle, then it means that the joint is non-existent, and that basically does not serve our purpose. We want to understand what happens when this joint exists. Okay. So takes that's one relation between x1 and y1. Now that also gives us a relation, and that also earlier we could have placed the robot at a certain x1 and y1, and we could have independently changed the orientation of the robot, of the link, if you say. So if I keep the robot here only, let's say at this point itself, but again I can, independently change the orientation of the robot and do like this, and maybe put it like this, right? So as the phi 1, that we can choose independently, even if I keep x1 and y1 fixed, because it was a degree of freedom at that time, right? But in this case now, if I enforce a revolute joint, then this angle, now this is the orientation, so this angle phi 1, now this cannot change independently. And what's the relation between phi 1 and the position of the center of mass? So basically this triangle can be formed, which I formed in the figure. I will draw it again here for clarity. So this angle phi 1, and this is the position of center of mass, so x1 and y1. So it can be written that tan phi 1 equals y1 by x1. Correct? Any questions at this point? Those who have joined little late, if you have any questions, please let me know. I will pause for a moment. Okay. I hope that's the case with all of you. So feel free to stop me and ask questions. Right. So we started with three independent variables, and now by enforcing one revolute joint, what we see is that we have gotten two relations among these variables. Right. So the first equation relates the x and y coordinate of the center of mass position, and the second relation basically relates the coordinates of the center of mass to the orientation of the link. So now if I just so if I know x1, right? If I know x1, then I know y1 as well as phi 1. right? That's the consequence of this. Just take a moment to, understand this. That now, by just specifying one variable, that is either of these, any of these basically, you can just specify x1, just specify y1, just specify phi1. We know the rest too because they are related. So let's say if I specify x1, then from this equation I can get y1, and once I know y1, from this equation I get phi1, right? Or if I choose phi1, then I get a relation between y1 and x1, and then I can write y1 in terms of x1. I get x1, and then from that I get y1, right? So these variables have become related. So the number of independent variables, right? So the key thing is number of independent variables. First case, without revolute joint. Those were three. And with revolute joint, it's one. And which means that one revolute joint takes away 2 degrees of freedom in the planar case, in a planar problem or planar system. Okay. Now you can do, or you can understand that a similar kind of argument can be given when we study the joint between the link 1 and the link 2, right? So there also similar constraints can be written. So two of the variables of the second link also now can be described in terms of only one, right? So that's what I mentioned here, that the first joint takes away 2 degrees of freedom, and the second joint takes away the 2 degrees of freedom, right? So two free links have total of 6 degrees of freedom, 3 plus 3, right? But a 2R manipulator has 6 minus 2 minus 2 equals to 2 degrees of freedom, right? So this is how you should think basically. So after when you have studied many such systems, and you have spent some time working with different kinds of robots, then you start counting degrees of freedom in a more intuitive way. So that would be in this case that uh, two revolute joints, that is 2 degrees of freedom, right? So the first link and the first. So usually what happens is uh, the independent variable, the natural choice of independent variable in this case would be phi1 and phi2, right? So phi1 and phi2, because these are revolute joints, that is, they describe rotation. So it's convenient to describe that, okay, which I discussed here, the first joint angle is 30 degrees, second joint angle is 60 degrees, and once you specify 30 degree and 60 degree, then everything else is known, right? So these are the two degrees of freedom of the system. And once you specify these 2 degrees of freedom of the system's configuration is fully defined and known. Okay. Let me just add a page here. Okay, let's continue. Uh, yeah, yeah. So let's continue. So now, like this, we can analyze more complicated systems. So one example system, which I will just quickly again uh, draw, is the uh, so just keep a note that this is page two. I think the order of pages will now be reversed. So yeah, degrees of freedom we are continuing. So let's say if I add one more joint near the base of the robot. Okay, so let me draw more properly a system. Again, a serial robot. So this is one axis, right? Then basically here is the second joint, and then there is a link. Oh, mm, yeah, here is the first link here, and then there is the second link, and they will write that joint like this. So yeah, so basically it's the same system, but one more joint I have added, right? So this, if I write it as J3 and J2, so if just J2 and J3 would have been there, then it would have been same as this. I have not drawn the axis correctly. Let me just correct this. Uh, Draw in the same orientation. Hmm. So let me draw in the same orientation. That this is the first link. This is the second link. This is the first joint. This is the second joint. And let's say I add a third joint here, right? And then there is a base. This is the fixed base, right? And this is the third joint's axis, right? So axis of these two come out of the plane. So this is Z2, this is Z3, and the axis of this remains in the plane, Z1. Okay, so let me draw the direction of rotations also so that you can imagine better. So this would rotate in plane like this would rotate in plane like this, and this would rotate the entire thing out of the plane. Okay, so let's say this is when the first joint is at zero angle, then the arm is in the plane, and then when I start increasing the angle, the arm would come out of the plane of the paper, right, and then rotate. So, so yeah, so just let me know how many degrees of freedom are there in this case. So here the number of degrees of freedom is 3. right? So corresponding to each of the three revolute joints, 1 plus 1 plus 1, right? Because as we have seen, uh, in case of the system, like adding one, so now the same argument of this planar case, like it's similar to this, the numbers would change because in a planar case, uh, this body is described can be described by three parameters. In a non-planar case, more number of parameters are there, but similar argument follows that we finally get a relation between those numbers, and finally the entire system's configuration or that joint's configuration can be described by one variable. So so this is theta 1, this is theta 2, and this is theta 3. So three revolute joints. It's a 3R because three revolute joints are there. It's a 3R, and what you would add in the description is 3R non-planar serial robot. Okay, 3R non-planar serial robot. Non-planar because now the end effector, now this end effector, it cannot just move in XY plane, it can move in XYZ all directions. Okay. Uh, and since we discussed joints, few other types of joints which are used but not as extensively as the revolute joints or are as common as revolute joints. They are the prismatic joints, right, in which basically there is the first body and then there is a second body, and basically the degree of freedom is translatory, right? So this D can change basically. The second body can slide in and out of this first body. Then there are, and here also, number of degrees of freedom is 1, right? Then there are spherical joints, right? Spherical joints are basically like a ball and socket joint. Okay, so it's like a, it's like joints that we find in our bodies, right, in many places. So here basically NDOF is 3, I believe. Let me just confirm. Yeah, so 3, right. So these are few other common joint types uh, that are seen, but revolute joints are the most common one. Okay. Uh, the lecture also covered some other distinctions, that is rigid versus flexible. In rigid robots, all the joints, oh sorry, all the links of the robots are rigid bodies. So rigid bodies means that they do not deform. There is no deformation in those links. But in many practical applications, links are made flexible, right? So they bend under loads and there is deflection in there. Uh, right. So now what I will do, I will come on to, yeah, these are joints that we covered. Yeah, so this is a list of joints. So revolute joint has 1 degree of freedom. Prismatic has 1 degree of freedom. Cylindric is one more, which has 2 degree of freedom. So here the joint can either rotate or slide inside and out. That 2 degrees of freedom. Spherical has 3 degrees of freedom. Right. Planar pair again allows motion in three directions. And hook joint is a kind of more special type of joint. It has 2 degrees of freedom. Right. Uh, Yeah, the common one again you would encounter is revolute, prismatic, and maybe spherical. Uh, yeah, so what's a link? As we saw, links are rigid bodies in three-dimensional space in the most general context. What we discussed right now was a 2D space, right? So they are described in 2D space, they are described by two translation and one rotation, so three parameters, while in the 3D space, they have a rigid body has 6 degrees of freedom. So XYZ rotation and XYZ translation and 3 degrees of freedom of rotation. So basically rotation about the x-axis, about the y-axis, about the z-axis. So three rotational degrees of freedom. So total 6 degrees of freedom are there, right? And this we will discuss in detail the DH parameters. I'm not just covering or going into it right now. Uh, yeah, so basically now what we can cover is, so we cover joints, right? And then how to basically actuate these joints, right? Actuate means how to, basically in simple terms, how to power these joints. If we have joints, then we have to move them in order to do something meaningful, right? And that's so the related word here is actuators or actuation systems. So actuators or actuation systems. Now, again, there's a whole lot of different actuators that can be used, right? And depending on the joint also, like for revolute joints, uh, we have like motors of different type, right? Motors like there are servo-based motors, which some of you might have used. There are stepper motors. Then there are BLDC motors, which are quite common in drones and legged robots, right? And basically many such examples. So all these that I just described, they come into this electric motors type of device, right? And other types are hydraulic and pneumatic. So hydraulic is basically based on using a fluid in order to actuate that joint. A common example of hydraulic device is if you have all seen those heavy machinery, let's say JCBs and all. So in the arm of that JCB that is being moved hydraulically, although that's not a robot, but an example of a hydraulic actuation system. And pneumatic is basically by using the flow of compressed air, right? The so in first case in hydraulic, as a special oil is used, and in case of pneumatic, compressed air is used, and third is using electric motors. Why electric motors are most common and most preferred? Because of their compact size and lack of additional accessories. So in hydraulics, basically you would need a lot of pipings, valves, and a whole fluid pressure management system to add in addition to your basically control of joints. In case of pneumatic actuation systems as well, you have to uh, have a system for you know controlling the pressure of the compressed air and reaching and basically pushing that air to those joints, right? And there are issues of leaks and lack of pressure, loss of pressure. But electric motors are quite, clean in that sense. They can be basically neatly compacted into uh, devices which have additional gearbox in front of them. So I will just give you a quick example of like the type of actuators. So or electric motors are one, and when I will add gearbox, that is mechanical, right? That is the mechanical component of it. So this basically forms our electromechanical actuators. And I will give you a practical example of an electromechanical actuators, again, borrowing from my experience on legged robots. So these robots that we build, these basically use uh, so they basically use BLDC motors, which are brushless DC motors, right? So they are BLDC motors, and then there is a shaft, and then we have a sun gear, and we have a three planet gears, right? So I cannot draw all three of them. I will just draw a front view. So this is the sun gear, and we have three planet gears, right? And we have a ring gear. Yeah, my drawing is pretty bad, but let me just put names. So this is ring gear, which is fixed. Some of you might have seen these gear trains. These are called planetary gear trains. So these are planets. These are free to rotate, right? So they can rotate about their axis. And the central axis, uh, the sun is mounted on the central axis, basically the motor's shaft. So this is sun, and this is free to rotate, right? Hello, do you have a question, Najia? Hello. Okay, no problem. Yeah, so this is called a planetary gearbox, right? So BLDC motor plus planetary gearbox, and this entire thing is basically encompassed in one single casing, right? Uh, and here is the output shaft, right? On which we mount the links. So this is the output connected to links, right? One more component is there, an electrical component, which is basically just an additional detail. So it's a motor driver, right? So it's you can imagine it's a PCB which is connected to the motor, right? And this is the device which controls how the motor should move, okay, to follow certain kind of commands. So not a topic of discussion right now, but just for general information. So basically, these three things are there in the actuator, from motor driver, which is again connected to the onboard computer from where the commands come. So motor driver, then the BLDC motor, and then the planetary gearbox, and then the output of the actuator. So this entire thing collectively is the actuator, right? And this is the setup commonly used in commonly used in legged robots, right? The benefit of these is, firstly, the most important benefit of this is that they have high torque to mass ratio. So torque to mass ratio is basically how much torque I am getting at the output, how much, let's say, peak torque can I get at the output, and what's the total mass of this actuator. So a higher torque to mass ratio implies that in a smaller mass, I can generate a lot of torque, and that always is beneficial because I can do different kinds of motions while also keeping my entire system lightweight, right? So that is one example. Uh, then there is a term, transmission, right? So uh, again, different type of motors are covered in the lecture, right? These are servo motors, drives, right? And then we have transmission, right? So now what's the purpose of a transmission, right? If people from mechanical engineering background might be familiar with this, right? People study these in their undergraduate courses. So transmissions. So the need of transmission is to basically, the idea is very simple. It has to transfer the power or the torque, right? Basically, the source of motion is from actuator, and it has to transfer that to certain link, right? So as I mentioned here, now there could be a case in which, right, there could be a case in which there is an actuator, right? There is an output shaft, and the link is directly mounted on this output shaft, right? So there is no need for a transmission in this case, right? But it's possible that due to space constraints or due to some very practical and crucial reasons, the actuator cannot be directly, or the link cannot be directly mounted onto the actuator, right? So let's say the actuator is here, right? And let's say I have to keep the link here. I have no option to take this link up here and mount it here, or I have no option to bring this actuator down here. Then how do I transmit the power from this output shaft to the link, right? So this is where this connection, what I keep inside this, right? This is where transmission comes in, right? So the purpose of transmission is to transfer power from actuator to the link, right? From the actuator to the link. Now, what are different types of transmissions that are there? Again, a lot of varieties are there, but they can be, let's say, belt and pulley, right? They can be chain and sprocket, or it can be, let's say, a four-bar mechanism, or it can be, let's say, a cable-driven mechanism, cable and pulley, right? So these are some common types of transmission that are used in the robotics domain, right? So transmission transfer motion to different joints and to different directions, right? Uh, and gearbox also comes in a, you can classify that also as a transmission as described here, right? So I will just quickly, you know, describe how a belt, let's say a belt and pulley can be used to serve as a transmission in this case. That might be interesting to some of you. So I'll just draw an image here once again. So use a different color. Right. So what we can do is basically, this is the actuator. So we mount one pulley here, right? And let's say for belts, so it's a, let's say if we're mounting a belt, so we mount a pulley here, right? And then we use a belt to again drive the pulley here, and this pulley is then attached to the link, right? So this is the output link, This is the basically the actuator. This is the pulley on the actuator end. So I've made pulley 1. This is pulley on the link end. This is pulley 2. And this is the belt. All right. Okay. So when the actuator moves, the pulley which is attached rigidly onto the shaft of the actuator, that pulley also moves. Uh, and if I draw a more closer picture of the belt and pulley, so basically, so generally belts have like some teeth like this, right? And basically the pulley has like teeth like this. So it so the friction is maintained properly. Okay, so these teeth engage with each other, and once the pulley starts rotating, the belt also starts rotating, and that in turn transfers the power from pulley 1 to pulley 2. Right. The key thing to ensure here is that we have to maintain an appropriate tension in the belt so that the power is transferred as much as possible, if as efficiently as possible from the actuator to the link, right? And similarly, in case of a chain sprocket mechanism, basically chain sprocket is something which you see in your bicycle, right? So the power source is your pedals, right? There is the power input, and from there, the power is transferred to your rear wheel, right? So there, the chain sprocket mechanism is used. Yes, Raju, you can answer your question if you have any. Motion will be. Can you just like explain a bit more in what sense you are saying motion will be decreased? No, you can design it in a way that still allows. So, what I understood from the question is that if we mount the link directly on the actuator, then the link can rotate 360 degrees. And if we basically go or mount a transmission, right, and then it might basically restrict the motion of the output link. But that won't be a case like in general, unless there is some other mechanical constraint that your link is interacting with some other part of your assembly, and they are like it's not allowing it to move. So here also, if this pulley is mounted on the actuator shaft, the actuator shaft can rotate completely one revolution, and when it rotates one revolution, this would make not one revolution here, because of course there is a if there is some gear ratio here, then it would move accordingly, right? But this link can freely rotate in this plane here, right? And this can rotate here freely. So there is no such loss of range of motion due to transmission, unless there are some other constraints in your system, not in general. Okay, all right. So yeah, so actuators we discussed briefly, and so we have discussed joints. Then we discussed how to power those joints. Those are the actuators, and just by adding these two things, so basically taking, let's say we have rigid bodies, those are the links. We attached two links together with a joint, right? So let's say that made our 2R manipulator, right? And I added motors on each of those joints. So at this stage, what I can do, I can power each of those motors independently, and I can basically move those two links. Okay, but to uh, basically make this robot uh, more practical, useful, or safe, right? What we need is sensors, right? So after actuators, the most important component of the robot is sensors, right? And you can always take analogy from your own body, right? So actuators in our body are our muscles, right? We actuate our joints. We actuate our joints using our muscles, right? And sensors are basically our eyes, ears, skin, and all these things. Tactile sensor, auditory sensor is the ear, visual sensor is the eyes, and we have nose, taste, all those things, right? So sensors, so basically they help in perceive the environment, but that's not the only thing that a sensor does. Perceive the environment or perceive the robot's own state, right? So environment and the robot's own state, these are two different things which I will just talk about for some time here to clarify the difference between these two types of sensors, because they both lead to separate directions of work also. So I will just first write two terms here. So first term is exteroceptive, and second term is proprioceptive. Proprioceptive. Uh, has any one of you uh, basically have heard or encountered either of these two terms before? Okay, no worries. So why I've written these two terms will become clear in a while. So sensors, the type of sensors that we attach on top of a robot or inside a robot, right? They are for two purposes. First is to perceive the environment of the robot, basically to know the environment in which the robot is working. And the second is to know the robot's own state, or I can use another word, configuration, right? And let's use an example of a arm itself, a serial robotic arm itself, to understand this distinction. Okay, so this is, let's say, a robotic arm. This is, let's say, a end effector which has, let's say, some gripper kind of a thing, right? We are not concerned about the degrees of freedom of the system here. This might have like maybe 4, 5, 6 degrees of freedom because I have drawn a gripper kind of a thing here. Okay, and let's say we have some objects here, right? Some objects here, and yeah, so this is it's a fixed base serial robotic arm. Why I'm mentioning the name of these, whatever robot that I draw, is that we should learn how to basically describe the systems that, let's say, you are working on, or or you have seen somewhere, right? So we should get into a habit of using these descriptions, that it's a fixed base which clarifies that this robot is not moving, and then it's a serial robotic arm, which again gives a clear idea of what will be the construction of this robot, right? And let me just use some other colors to, yeah. So now, just let me know if I want my arm to go pick this thing, right? To come here, right? And let's say grasp this, right? So What kind of sensors do I need to have? Can somebody just guess or maybe make tell something from their intuition? Like what type of sensors should I must have in order to do this, or would be good to have in order to do this? Can you repeat? Sorry, I'm not able to exactly understand. We can write in the chat box. That would be better. Maybe there's some issue on my end, but I'm not able to understand you. Could you please write this your answer in the chat of the meeting so that I can just read it? Oh, UV sensor. Okay. Yeah, that's one good suggestion. That's one good suggestion which might be useful. I will write that down. Like there are much better options, but I'll just write that down. Motion sensor. Oh, motion sensor. What do you mean by a motion sensor? Can you like this term exists, but I'm not exactly sure what are you trying to convey by saying a motion sensor. Can you just describe it? Siddharth, I guess Siddharth. PIR motion sensor. Okay. Again, these are not exactly appropriate in this scenario, but yeah, these are sensors that exist, so I'm just writing them. These are used in other scenarios. Yeah, I think we are the very, I think I thought the obvious answer that would come is a camera, right? Why not use a camera, right? One of the most commonly used sensors. Again, it's not that it cannot be done without a camera, but camera is, I would say, the best choice here, and it's an optical sensor. Okay, so yeah, some of you suggested some things. So I will describe with the camera. Okay, so let's say I mount a camera on the close to the end effector here, so that the arm basically has a now has a view of what's in front of the end effector or the gripper, right? So, or maybe I can also maybe I can also if let's say this is a lab kind of a setting, then I can also have a frame here which has cameras mounted on those frames, right? So from this camera I can detect where is the object lying, right? That can be done. So what does this sensor tell? It tells the robot that in its environment, in its surrounding where it's supposed to do certain task, either it tells us about the object of interest, which is in this case a box, and it would also tell about, let's say, other things in its environment which it might need to avoid, right? So basically obstacles or things in it which it can collide into. So all this information about the environment can be given by, let's say, a camera, or that can be also be done by, let's say for a mobile robot which needs to avoid obstacles, a UV sensor is perfect, right? So so all these sensors that we discussed here, they help the robot, any robot, either be a fixed base robot or a mobile robot, perceive the environment, right? Environment is something external to the robot, right? So so environment is external to the robot. It's not a part of the robot itself, right? if i place the robot uh, if I place the robot in, let's say, a dark room, then a camera won't be needed, then based on that environment, I would have to change the sensors, right? Some other thermal sensors, IR sensors I would have to use. So these type of sensors depend on the environment in which the robot is working or being used in, right? And the type of application that the robot has to uh, do basically, right? And the common examples, a couple of them you have mentioned, and then basically cameras are also of different types. Commonly used is RGB depth camera. These are stereo cameras. Then there are lidars, right, which basically use laser beams to detect the surroundings. And yeah, basically IR sensors, the UV sensors. There are sonars, right? All these sonars, radars, all these sensors, they all help the robot to map its environment, to know where it is, right? What's lying around it, and maybe then decide what it needs to avoid, where it needs to go, what it needs to pick or manipulate, right? So all these sensors are called exteroceptive sensors. Exteroceptive, right? So this ceptive is like borrowed from the term perceptive, like to perceive, right? And extero, you can imagine like external, right? So external perception, exteroceptive. So that I think is usually well understood by most of you. The other class of sensors, right? So continuing with this example itself, right? I have my camera, I see the object, and let's say I find out that, uh, let's say X, Y, Z is the coordinate of the object, and now I have to move my end effector to this place. Now, can any of you uh, know or suggest that for moving reliably or precisely to this point, does the robot need any sensors, or it can do without sensors also? You're saying it can do without sensors also, right? Okay, yeah. So yeah, that's one option, right? So what you can do is you can uh, maybe calculate what are the angles that need to be commanded to the motors, right? And you just command those angles to the motors, and the motors would, and you hope that the motors are accurate enough that they move precisely that amount, and you hope that your end effector is in a perfect position to hold on to that object. But the reality is not so perfect, and in that scenario, it would happen very likely that you might be off from where you want to be, right? Let's say you wanted to be at 2, 3, 5, but let's say you are off by a few centimeters, or yeah, in some directions depending on the accuracy of your actuation system, right? So and this is one example where it can still manage itself. This is a fixed base manipulator. In case of mobile robots, let's say, going back to legged robots, let's say a quadruped, a robot dog, right? In order to uh, move those more complicated systems, right? The robot needs to know where are its joints or its links located in space, right? So I would repeat that again. The robot, either be this fixed base or a mobile robot or a floating base robot, the robot needs information about what's the position of the joints of its own joints, right? Or what is the orientation of its body, right? So these are all information about the robot itself, right? It's not concerned about whether the robot is in a dark room, is in a well lit room, is working in sun or working in night. This is concerned about the robot's own state, own configuration. It's information about the robots, let's say in case of a 2-hour manipulator, it's the information that robots need about what are the actual joint positions, joint velocities, that it's experiencing or it's in currently, right? So this knowledge, this knowledge about the robot's own degrees of freedom, right? That is called as proprioception, right? And the sensors which help us achieve this, they are called proprioceptive sensors, right? And here the two common sensors that are used are joint encoders, or basically encoders. These are for angle measurement. So in revolute joint, to know to know all about the angular information of the joint. So basically, joint angle, joint velocity, right? All these things. Then the other is inertial sensors. Inertial sensors include, or also known as, the IMU. Have you heard about the IMU? Inertial measurement units, which basically have accelerometer, gyroscope, and sometimes a magnetometer. A magnetometer, right? So, so joint encoders would be used in, let's say, these. Getting back to this example, if the actuators that are being used here have joint encoders, right? Then as the robot moves, I will know what is the actual position of the joint, right? So let's say if I commanded the arm to, or the first joint to move by 5 degrees, and let's say it just move 4.5 degrees, then I know that I am off by half a degree, and then I can use that information to further correct my position, right? Or similarly in the case, or correct my velocity, right? So that information helps us to achieve this target of XYZ, that can help us reach that target more accurately and precisely each and every time, right? Because we will be actively using knowledge of my own joints, right? The robot would be using the knowledge of its own joints to basically correct its motion, right? So, and why inertial sensors? So inertial sensors are not so relevant in case of fixed pace uh, robots, but in case of mobile robots, inertial sensors are very, very crucial, and they are used in all the mobile robots, right? Because they tell how fast the body of the robot is moving. That is basically the task of the accelerometer, right? To detect or to give the measurement of the acceleration in the XYZ direction. So how fast it is moving, or whether it's pushed by something or it has collided something. So all that information. The gyroscope tells about the orientation of the torso. So let's say if the robot is on an inclined surface or has toppled, and now it's in a configuration from which it should take some emergency action, right? So all this information about orientation of the robot or any body on which the IMU is mounted. So that is given by the gyroscope, right? So these two information is also needed by, especially by mobile robots, to function properly, right? Otherwise, let's say if a robot does not have mobile robot does not have IMU, right? Then it won't know if it's standing upright or it has fallen down, right? Because it has no information about its orientation. Okay, so they are very crucial, these proprioceptive sensors. In fact, whenever we start developing or building these complicated robots, we first use proprioceptive sensors because they are necessary for, and it cannot be like it cannot be done like I will add joint encoders or IMUs later and I can just move my robot or use my robot. It has to be there in the hardware right from the starting, from the beginning, right? So if let's say you start uh, developing your own robots, then first thing that you should understand or take a call on is that, do you need any proprioceptive sensors, or if you use proprioceptive sensors, would it help your application? And then first integrate those sensors. The exteroceptive sensors come later when the robot is able to basically, so in case of an arm, the basic function of the arm is to move its joint reliably, right? Even if it's not doing a pick and place operation. Let's say if I want my arm to move 5 degrees in the first joint, 10 degrees in the second joint, and if it's able to achieve, let's say, 4.9 degrees and 9.9 degrees, or even better, right? That is the first target, and for that, a proprioceptive sensor, that is a joint encoder, would be needed. Once it is able to do that, then I am sure that if I command the correct angles, the robot is bound to follow that to achieve those angles. Then the second part of the this example comes in, that I mount a camera, I figure out the position of the object of interest, I figure out what are the angles I need to reach in order to reach that position of the end effector. I plan my trajectories and I follow those trajectories to reach there. Right. So the exteroceptive part comes later. Right. And again, so since proprioceptive sensors are knowledge about the internal states, they do not depend on the environment the robot is going into. So whether it's again any different kind of environment the robot is exposed to, uh, the same set of proprioceptive sensors would be on the robot and would be working. Right. So, any questions at this point about usage of proprioceptive and exteroceptive sensors, and what's the difference between them? Okay. Yeah. So this is what is mentioned here as in more simpler terms, that is internal and external sensors. So internal sensors are equivalent to proprioceptive sensors, as I mentioned, and external sensors are the uh, basically the exteroceptive sensors. The internal sensors measure the position, velocity, the torque, as I mentioned, and external sensors, they measure the proximity, the slip, the vision, and all those things. So, in fact, just just something you can think about, and maybe now that you know about proprioceptive sensors, you can understand it in a better way. So, when you walk in, when you, let's say, walk blindfolded, or you're walking in a pitch dark room, right? There, what you are using mostly is your proprioception, right? So, proprioception happens in your body itself, right? Your body has sensors that tell whether the body is upright or body is lying down, right? So even if you have no visual feedback, no auditory feedback, you can still walk properly and move properly because you have proprioception. So again, different sensors were discussed in the lectures. I would not go into details of them, right? Because these you can directly read. Yeah, so at this point we have discussed that rigid bodies combined together using certain types of joints, adding actuators on those joints, and adding all the relevant sensors, and you have basically what broadly constitutes a robot, right? So once we have that understanding, now we can move on to the understanding the maths of these systems and how to basically describe these systems mathematically so that we can derive their equations of motion and develop control laws and basically control how these robots can move and finally be used for some applications. So what I would do now is degree of freedom we have discussed, and we can I think start with kinematics, the brief description of what is kinematics and dynamics. Okay, yeah, maybe I'll just use the remaining time to describe forward kinematics and inverse kinematics. Okay, any questions before I start on the modeling part? Because yeah, then we would be in that modeling would be extended discussion. It would be covered in different many different weeks basically because we would first discuss kinematics, then dynamics, then control. Right, so yeah, let's get started with it. Modeling and analysis of robots. Okay. And here the key assumption would be that we have rigid bodies. Unless otherwise specified, all the links in the robot are rigid. Oh, Siddharth, I missed your question. Uh, yes, Siddharth, you can use our Arduino to control a robotic arm. Yeah. Encoders, yeah, so encoders are basically devices which which calculate the amount of rotation that has happened, right? And there are different type of encoders. There are absolute encoders, there are relative encoders, right? So and they are based on different type of concepts, right? So as you mentioned or as you have seen, there are optical encoders and there are like magnetic encoders. So let me just quickly go through here. Hmm. So optical encoder basically has a transparent disk with a pattern, right? And as the motor shaft rotates, this disk also rotates. And basically, what happens is that this LED and this photodiode, the light intermittently passes through this strips, and then again it gets blocked. So in a way, it is like counting that how many of these equispaced strips have passed by, right? So let's say I have 20 of these strips on around all around the circle. So the angle between each of these strips would be 360 by 20, so that's 18 degrees, right? Just a rough example. That's 18 degrees, and let's say if if the diode gets activated once, that means one strip has passed, right? So that means uh, that the basically the motor has revolved that rotated by 18 degrees. So actually, in reality, it would not be this coarse or this big a angle. It would be more fine angle that can measure. But that's basically the idea. So the idea of encoders is that it measures angles, right? And I think magnetic encoder is not mentioned here, but that's the one which is primarily used in all the robots. So you can read up more about that. Magnetic encoders basically used change in magnetic field of like in the due to the rotation of the motor and the magnetized magnet. So there is a magnet also there, and I I do not like recall the exact working principle in detail right now, but you can read about further about magnetic encoders. They are slightly like I would say more uh, complicated to understand, but they are more reliable and give more accurate information also, right? And the difference between absolute encoders and relative encoders is that absolute encoder basically basically tells the absolute position of the shaft, right? So uh, wherever and like wherever is the zero, so from that position how much the shaft is rotated, that information you can directly get. In relatives encoder, it's basically that we have to specify that reference of zero every time that we start using the robot, right? So this is something as known as calibration. So we have to specify that this is my zero position of the joint, and once that zero position is recorded, then after that how much we have moved in what direction, and that is basically given by that relative encoder. So, Siddharth, let me know if I have like just briefly cleared your doubts. These are something which you can read in much more detail in books and like online articles. Yeah, so coming back onto the modeling. So, yeah, so modeling, before we start modeling any robot, we need to know how many degrees of freedom are there, right? Types of joints, right? Then what we would need is we would need kinematic parameters. Parameters, I'm saying. So this is I'm listing down what all information do we need in order to model a robot, and then we need dynamic, or I would say I should write I should write inertial inertial parameters. So and throughout this discussion, I will use uh, the go-to example of a two-hour manipulator, right, which has link L1, L2. These are lengths of these links from now on. This is mass is m1, m2. The inertia is moment of inertia is I1, I2. Right. This is joint one. This is joint two. This angle is theta one. This angle is theta two. This is the x-axis. This is the y-axis. Okay. So let's first gather these information for this system itself. So number of degrees of freedom is 2. Type of joint 2R, two revolute joints. Now kinematic parameters are basically related anything related to dimensions and lengths, widths, heights of each of the links, and range of motion, allowed range of motion basically. So all these are kinematic parameters. So it's like the length of the links here, L1, L2, and maybe if I let's say specify certain range of motion, so it may be like theta 1 min, like it's usually robots do have constraints on how much they can move their joints. So no, it would be theta 1 max, and then maybe theta 2 min and theta 2 max. Right. These would be the kinematic parameters, and inertial parameters can be are something related to the equations of motion. Like basically think of Newton's law and Euler's law and how the parameters that occur in those equations. So basically masses and inertias, right? So these all come in the inertial parameters. And for right and for now, like for simplicity, I am considering the joints as frictionless. So I'm not considering like stiffness or damping in the joints. But for real systems, that's also something which we need to model if we want to make the model more accurate. Right. So now the two common things which we do for any robot is kinematics and dynamics. Right. So what is kinematics? So kinematics is the study of robots' motion. Right. Right. And dynamics is study of the cause of the motion or motion with also understanding the cause of the motion. Right. So here we are concerned till like position, velocity, or let right. And here we are like concerned about accelerations, forces, moments, or torque, which you can say. Right. So that's the key difference in kinematics and dynamics. So when I'm saying that I'm doing a kinematic analysis of a robot, that means that I am trying to find relations which relate the degrees of freedom and my independent variables to how the end effector or any point of interest on the robot is moving, is changing its position, its velocity, right? And when I say that I'm doing a dynamic analysis or dynamic modeling of a robot, then I mean that I am deriving relations which basically relate, if I have to accelerate a certain link, uh, then what's the forces that I need to apply, or what are the torques that I need to apply on the joints, right? So that's the key difference. And then in both this kinematics and dynamics, there are two more terms, again, very fundamental to robotics. That is forward problem and the inverse problem. Here also the forward problem and the inverse problem, right? Now, so yeah, basically this is something that I would wrap up with today. What is forward kinematics, inverse kinematics, and what is forward dynamics and inverse dynamics, right? So we have, so before I discuss that, as I mentioned, we have the degrees of freedom. Let's say in case of a all revolute joint robot, right? So it would be theta 1, theta 2, and theta n, let's say. Or in a more generic sense, I can write the joint variables. The joint can be anything, revolute, prismatic, anything. So I can write as Q1, Q2, Q3, right? So these are in the space we call as joint space, right? Joint space. So collection of all the degrees of freedom, those independent variables, they lie in the or they form the joint space, right? So for a 2R manipulator, so the joint space is basically a vector theta and theta 1 and theta 2, right? The joint angles. Uh, and the other is basically what I can describe as x. And this is basically the task space or the Cartesian space. Uh, Task space or Cartesian space. Right, so this basically this can also include orientation, right? So this is basically description of the end effector. Why I keep saying end effector? Because that's usually the point of interest which we are concerned about, right? So for a robotic arm, it's the end of the arm that we are concerned about mostly. But sometimes we might also be interested on some any other point on the robot. But what's the so this is called the task space, so or the end effector space or Cartesian space, right? So this is basically that what is the position and the orientation of the end effector, right? And this can at max have six elements: the position three, and the orientation three, so six. But the degrees of freedom can be any arbitrary, like two, three, four, five, n number of degrees of freedom, right? In the joint space. Now the forward kinematics and the inverse kinematics that is related to this concept, right? So forward kinematics, FK. FK takes the joint variables and gives me the value in the task space, right? And the reverse is done by IK or the inverse kinematics. So this is FK, this is IK, this is FD, and this is ID, right? So for the 2R case, knowing theta 1 and theta 2, calculating the x and y coordinate of the end effector, right? So that is forward dynamic problem. And wait, I should not put vector symbols here. These are scalars. P is a vector. Yeah. So going knowing theta 1 and theta 2, the joint angles, and then using some relations calculating what is the position of the end effector, that is forward kinematics. And the reverse problem is knowing the position of the end effector, finding out the joint angles, right? So in inverse kinematics, P is known, calculate theta. And in forward kinematics, the reverse happens. And we keep using both of this in our modeling of robots, right? And similarly, we have forward dynamics and inverse dynamics. So in forward dynamics, we know the joint torques and we calculate the joint accelerations. And in inverse dynamics, we know the joint accelerations and we calculate the joint torques. So here this is calculated in forward dynamics, and in inverse dynamics this is calculated, right? So as you can understand, this is the cause and this is the effect. So in forward dynamics, cause is known and we use relations or the equation of motion to know the effect, right? And in the reverse case, the effect is known, or the effect that we want to have is known, and then we have to calculate the effort or the cause, right? That if I want my joint to accelerate uh, for 2 radian with an acceleration of 2 radian per second square, then what is the joint torque that I need to apply? Like that is the inverse dynamics problem. Wait. I think. Wait. Wait. I missed between these two. This would be the arrows would be changed, or this would be changed. So this is the inverse dynamics problem. My bad. This is the forward dynamics problem. Right. In forward dynamics, we know the accelerations, and we calculate uh, the required forces. And in inverse dynamics, we know the cause, we know the torques, and we calculate the outcome of or the effect of those torques, that are the joint accelerations. Right. So this is what you would see being discussed in this lecture slide also. Uh, yeah. So direct problem is obtain motion of the links uh, given the applied external forces and moments. And inverse problem is obtain joint torques and forces desired for the required for the desired motion of the links. So I think okay. Let me go over this once again. Let me draw this once again. The kinematics part is clear to everyone, I believe. Let me just describe the dynamics part once again. I will redraw these things. So the direct problem is, or the forward problem is, obtain the motion of the links given the applied external forces and moments. So what is known is the torques, or torques. When I say torques, I mean to include both forces and moments. Right. So we know that information, and we have to calculate the accelerations. So once we know accelerations, we can integrate it to calculate velocities and then to position. So we obtain the motion. Right. So forward dynamics is, which what I draw previously basically was correct. So forward dynamics is going from torques to accelerations, and basically accelerations will give velocities, velocities will give positions, right? And the inverse dynamic problem is, when these are known, then what is the required thing to cause these motions? So here this is this is calculated, and here this is calculated, right? So that is consistent with the definition in the slides as well. That inverse problem is obtain joint torques forces required for a desired motion of links. So desired motion of links is given by knowing of q double dot q dot q, and we solve the inverse dynamics problem to get the desired forces and moments. And in forward dynamics problem, we know the desired forces and moments, and we calculate the motion of the links, which is given by the accelerations, the velocities, and the positions. So any questions at this point in the forward and inverse problem, especially in dynamics part? Okay, so I'll I'll not start anything new at this point. Uh, I will just quickly summarize what we have discussed in this session. So so we started with what are robots, what are different types of robots, series, parallel, floating base robots. Then we discussed about the degrees of freedom, and then we saw how basically when individual bodies which have you know more degrees of freedom, when they are connected through joints, then the eventual system that has lesser degrees of freedom, because joints put constraints, and constraints reduce the degrees of freedom of the system, right? And then we mathematically saw how we derived for a planar case, for a 2R case, that how the 3 degrees of freedom of an independent link is reduced to only 1 degree of freedom when it is connected to a fixed base through a revolute joint, because now the three independent variables are connected or constrained by two equations, and each equation takes away one independent variable. So basically, the degree of freedom that remains is one, right? And then we discussed basically what are different joints that occur in typically in a robotic system, that is revolute joint, prismatic joint, and spherical joint. And you can do the degree of freedom analysis counting by just counting degrees of freedom corresponding to each of these joints. So for revolute it's one, for prismatic also one, for spherical is it's three, right? And then how to actuate or power these joints. We discussed about actuators, and I gave the example of a actuator that is commonly used in legged robots that has a BLDC motor, a gearbox transmission, and finally the output is taken after the gearbox. We also discussed about transmissions and what's the need for transmission, basically uh, to uh, take the power from the actuator to the output link uh, at a different location, and also maybe change its direction. There are different types of transmissions: belt and pulley, chain and sprocket, and four-bar mechanism. Right. Then we started discussing about sensors. We discussed about exteroceptive and proprioceptive sensors. Basically, exteroceptive sensors perceive the environment and they are related to the kind of application that the robot needs to do or maybe move better in a certain environment. But proprioceptive sensors, especially for mobile robots, are very crucial and needed. Right? They tell that what's the internal state of the robot about its own orientation, its acceleration, and position of the joints. Uh, and then the different sensors that lie in these categories. And finally, we started the modeling and analysis of robots. So we start with the information about what's the number of degree of freedom, the types of joint that are there, and what are the kinematic and inertial parameters. Then we discussed what is kinematic problem, what is the dynamic problem in context of modeling, and then the classification of the forward and the inverse kinematics and dynamics problem, which we will start discussing in subsequent sessions. So if you have any questions, you are feel free to ask me now, or you can maybe uh, reach out to me later, maybe comment on the YouTube videos, or maybe in the forum discussion. Uh, yeah, so if we do not have any questions right now, then we can end this session. Uh, I think Siddharth, you have the information on the NPTEL site, uh, or you can basically, I would be posting this video on the YouTube channel, which would be there accessible to you, and you can directly ask your questions there also. Okay, then see you guys in the next week session. Goodbye.